So let's actually calculate a cell potential. We'll label this as a capital E cell. You may also see it as a fancy E, I think it's an epsilon cell. This is our potential difference between the two electrodes, and it depends on how much things want to be oxidized or reduced. So the relative tendency of reactants to undergo oxidation or reduction. It also depends on temperature and concentration. So we will start under standard conditions, which is 1 molar concentrations, 1 atmosphere of pressure, and 25 degrees Celsius, which means we can add a little circle and have E with a circle cell. So let's compare the reaction of zinc solid with copper 2 plus to make zinc 2 plus and copper solid. We're going to compare this to nickel solid reacting with copper 2 plus to make nickel 2 plus and copper solid. So in both cases, we have copper 2 plus turning into copper solid. The difference is that the top reaction is with zinc and the bottom reaction is with nickel. The top reaction has a standard cell potential of positive 1.1 volts, and the second reaction has a standard cell potential of positive 0.62 volts. So a larger value for the cell potential with zinc. What this means is that zinc has a higher tendency to be oxidized than nickel, right? Zinc is being oxidized. The potential value is higher when zinc is put with copper. Zinc has a higher tendency to be oxidized. So this standard cell potential is for the whole cell. It's for the entire thing. It's for that whole reaction, the entire thing together. But if you've looked in the appendix, you know that cell potentials for the cathode and anode exist individually. So the question is, how do we get those? We get them experimentally, and we get them by referencing them against a standard. So we have chosen one half cell, one half reaction to be the standard, and then have referenced everything against it. So it is the standard hydrogen electrode, so you'll see it abbreviated as SHE, as 1 molar hydrochloric acid, 1 atmosphere of hydrogen gas, and a platinum solid electrode. When we reference it, we always make the standard hydrogen electrode the cathode and set it equal to 0. So the cell potential for the cathode is 0 volts. The reaction that's happening is H plus getting 2 electrons to make H2, right? It's always the cathode, so it always has to be reduction. An example cell, if we put solid zinc and zinc 2 plus aqueous in a cell, right? I've got this is my shorthand notation. I've got a salt bridge in a cell with the standard hydrogen electrode, and we measure the voltage. The standard cell potential is 0.76 volts. So this is for the entire cell. This is what we've measured. Well, I mean, we have two things going on here. In the cell, this is a potential, this is an energy. We can do final minus initial, which is really cathode minus anode. And we have stated that the cathode, which is our standard hydrogen electrode, is 0. That is our 0 point. This is our reference against it. So the standard cell potential is the potential of the cathode minus the potential of the anode. If, with this being true, because I measured a positive 0.76 volts for the entire cell and the cathode is 0, then my anode must be negative 0.76 volts. My anode was at a higher potential energy than the cathode, so I got a positive potential value for my standard cell potential, And a positive value for the cell potential means that it is spontaneous or thermodynamically favored under standard conditions. So every value in the appendix comes from this type of experiment. That half cell, that half reaction was set up against the standard hydrogen electrode. The standard hydrogen electrode was set as the cathode, and we measured the voltage and calculated what the potential would be for the other side. Now, in the appendix, where they are listed, here's some examples of how you'll see it listed. Zinc 2 plus 2 electrons turning into solid zinc with a standard potential of negative 0.76. Copper 2 plus 2 electrons turning into solid copper with a standard potential of plus 0.34 volts. All of the electrode potentials are written for reduction. So these are reduction potentials. If that reaction is not the reduction part, which it wasn't when we set up the standard, because we made the standard hydrogen electrode the cathode, we have to change the sign. So if the zinc reaction, for example, is the anode like it was in where we started, then the sign would get changed. But our equation does the sign change for us. So all we have to do if you're doing cathode minus anode, take the values from the appendix, plug them in, and the potential that you get will reflect the fact that one is oxidation and not reduction. So our example, we're going to calculate the standard cell potential for this full reaction. From this full reaction, there's a lot going on. We will have to pull out what is oxidation, what is reduction, get the standard cell potential values, we'll get the standard electrode values, and then plug them into our equation to get the potential for the entire cell. So lead, what is this? Lead 4 oxide plus 4H plus tin turning into lead 2 plus 2H2O plus tin 2 plus. So my oxidation half reaction is tin turning into tin 2 plus and 2 electrons. The reduction half reaction is lead 4 oxide plus 2 electrons turning into lead 2 plus. And then we have to go to the appendix and look up what values exist. So tin 2 plus 2 electrons turning into tin, right? This is written as the reduction form because that's how it appears in the appendix. The standard potential for this electrode is negative 0.14 volts. And then the lead 4 oxide plus 4H plus 2 electrons making lead 2 plus and 2 waters. The standard electrode potential is plus 1.46. So cathode minus anode, 1.46 minus a negative 0.14 gives me a standard cell potential of 1.6 volts. This cell would be thermodynamically favored. It would be a galvanic cell. It would be spontaneous as written.